Hello. So I put my first slide up early so that my entire talk and all the notebooks that I'm going to go through are actually at this Git site. So you can just go there and GitHub nicely renders them through its auto NVVer now. In fact, that's how I'm showing them now. So I will put this up, and it's also going to be at the end, so you can, if you didn't get them now, you can look at it later. All right, let's go here. Okay, who am I? So I'm a former quant. I work at Continuum now on various projects. Interestingly enough, that actually provides a lot of fodder for thinking about like various problems that companies have and how they go about solving them. And invariably, they go about solving them the wrong way, but I try to help them. And in fact, a lot of these ideas got propagated back into Pandas as well as a bunch of other open source projects. I've been working on Pandas I've been contributing to Pandas for 5 or 6 years. And I've been a core committer for maybe the last 3 or 4 years, and I've been maintaining it actually for the last couple of years. All right, next slide. Okay, so in general, what do we care about when we're writing code? So we care about the feature set. If we didn't have features, we wouldn't have code. Basically, we want the software to do something useful. Of course, along with these features, we want things like, we want to have readable code, we want to have testable code, documented code, and we want to be able to have other people actually maintain it. So Pandas helps with this a teeny bit, mainly with the readability, actually. You can basically do a lot in just a few lines of code, which is great. However, there's lots of constraints when you're writing code. How long does it take to write the code? And, of course, what seems to be everybody cares about, how long does it take to run? Further, people care about things like resource utilization, maybe how much space does it take for the hard drive to use it, or how much memory space does it use? These are all important things. I'm not going to talk about anything today except for the runtime and the resource utilization, mainly things about memory performance. Okay. Let's see here. Okay. So, what drives Pandas? This is just going to be a quick peek into the internals, so you can understand how things work a little bit, and then you can understand where performance comes from or does not come from, actually. So Pandas is basically a superset, or is basically uses NumPy as a backend, okay? And I'll get to this in a second when I discuss the other backends that we use. So the principle is we have D-type segregation, and this leads to a block memory layout. So in other words, I'm going to show you my first thing here. So let's take a typical, here. So take a typical data frame. Can everybody see this okay? You make a data frame with a couple of different D types in it, and you have a pretty data frame. Now, you'll notice that you have your different D types, and this is just printing them out in the order that I inputted them. However, if you look under the hood, sort of raise the skirt a little bit, you'll see that actually this creates what's called blocks, and these are all happen to be, they're all two-dimensional blocks in this case. And the only one that's interesting is the float block here. This is actually, it's comprised of both the B and E columns. And so they're aggregated, they're consolidated is what I call them. So each different D type is represented as a block, and these are all NumPy arrays. Whereas if you have different, even if you have different columns of the same D type, they will actually be smushed together. So this leads to an interesting performance implication. Number one, it allows you to do fast row aggregations, okay? This was one of the original use cases for Pandas, is you can take your table and you can go really fast. Why? Because you're using NumPy under the hood. Great. However, this actually leads to sort of a problem if I want to continuously insert columns. Now, I'm not going to say you should do this. In fact, I'll say this is on my don'ts list. If you start adding columns to this, what happens is Pandas will so-called consolidate them. So basically, this involves a copy, okay? So this is something you shouldn't do. And I will get to that in a second, okay? All right, so these different block types, right here. So this is a nice little picture. It looks like a D-type hierarchy because that's exactly what it is. These represent all the different types that Pandas can store at the moment. The yellow ones are so-called concrete types, as are the little green ones over there. I'm not going to really go into this in detail. This, if you think about it, this follows the NumPy D-type hierarchy as well as the Python D-type hierarchy. These are some actual future ideas, things that we're going to add, different ways of storing data. So in other words, you can basically store data, and if we have a block to represent it, we can make it very efficient. So here's an example. Everybody knows, date times are quite efficient in Pandas. That's true. However, date times, if you have a time zone attached, are not efficient at all. Why? Because they're represented as an object D type. And as everybody knows, NumPy just represents object. Essentially, it's a pointer to a Python object. So you can't represent these as base scalar types. Okay? However, once I do that block, then we'll be able to do this. Okay? So essentially, you'll be able to represent the data in a very efficient form and work with it, but it will be, we're going to sort of trick NumPy, and we're going to say, okay, let's represent our data this way as very efficient datetime blocks, but we'll have a little attribute for time zone. So this is not done yet. This is why it's in grayed out. Other things that are on the roadmap is integer NA, and I know nobody likes to have this. This will hopefully happen soon. We need some support from some other libraries to do this. All right.
Jeff,
yes.
How efficiently are the string handling?
We will talk about string handling in depth in a little bit, okay? Because that's important. Okay. Oops. Did I go? Where did I go here? We'll get to that in a second. Okay. So, I said before that Pandas uses NumPy as a computational backend. It uses it as a storage backend, okay? But it also uses it as a computational backend. In other words, when you do sum, what do? We actually have a sum, believe it or not, but we almost always will we will delegate back to NumPy to actually do the operation. And there's some cases where we won't do that, and I'll go through them. So let me give you a little next slide here. This is a picture I did a while back for the so-called PyData ecosystem. Note, I left out SymPy accidentally, and I also left out Numba, so these in blue here are the so-called computational backends of Pandas. NumPy obviously is the big one here. We are going to talk briefly about Bottleneck and NumExpress. And these are what I call highly recommended dependencies. In other words, they're not required, but you should really install them because you get a lot of stuff for free. So, did I put this one up here? Yes, okay. So note in my notebooks, I usually do some stuff. I like set options, max row, just to, not display too many rows. Okay. So what is NumExpress? It's just an open source library that basically takes advantage of, it basically translates a string-like expression into its own internal abstract tree, executes it, and it can beat NumPy in a lot of situations. Why? Because it tries not to use temporaries. Okay. It'll just simply evaluate the expression. It'll take vectorized expressions, evaluate them kind of like a ufunc does, but it will do it without all the intermediate steps that NumPy does. Great. It could also take advantage of multi-core, and we'll talk about that at the very end. But the point is, if you have an expression, and this actually is a fairly large expression here, we're doing a Boolean operation, and I will get to this in 1 second, but the first thing I always do is assert that my two comparisons are correct. In other words, they're equal to each other, because there's no point in comparing things that do different things, and this is one of my pet peeves, and we'll go over this as well, but suffice to say these give equal results. Here's the two time-its. This is when I say in Python, this is just simply what I call singular evaluation. If you actually worked up the abstract tree here, this is actually 3 operations here. So we have, df1 is greater than df2, put it in temporary. We have df3 greater than df4, put it in temporary, and then do that result again. So we have 3 operations here. NumExpress can do them all at once. Great speed up. Awesome. This is done automatically for you. Basically, every expression actually is first tried on NumExpress. Not everyone, but if it's D-type compatible, it just hits NumExpress first. You don't have to do anything. Keep in mind, this only really works for things like floats, ints, bools. It has to be a C representable. Strings do not count. Certain datetime operations actually do count because we do some internal translations. Okay. The other library that we use internally, again, it's a highly recommended dependency, is Bottleneck. Again, this will be used if it's installed, so install it. It's basically for free. In effect, it does sort of what NumExpress does on a vectorized level. It does this on well, I shouldn't say on a scalar level. It has very fast and very specific functions to do things as simple as sum or nan sum, and it does it faster than NumPy. How does it do that? Well, it's very tight, customized code that has been exposed to Python, and it selects the exact routine for this shape and D-type you're passing in. Okay, sort of think of it as like a fuse type everything, and it picks exactly what you need. It's very fast. So here's some comparisons, and in this case, I actually have to physically turn off bottleneck to show you the result, because otherwise it will be used automatically. So you can get some modest speed up, and of course your mileage will vary on various types of data sets. Okay, next. All right. Okay, the last thing that drives, the last two things that drive Pandas internals, we use Cython for a lot of the internal computations, namely the most prevalent of being group bys. This is all pure Cython, and it just comes with Pandas. Makes things fast. We also have a hash table implementation that drives a lot of the indexing. Okay, and this I'll show you a little teeny bit later. Okay. All right, next. Okay. So how do we make Pandas perform? Aside from read Ian's book, have correct code, then you want to profile and compare it. So these are very important steps. And then rule number 3 is refer back to rules number 1, because this is an iterative process. You basically make a change in something, and you're like, oh, because I can't even tell where good performance comes from. I can sometimes, but I always profile, and I'll just keep hitting this, that you want to have correct code, and then you want to profile, and then iterate. Okay. When you do comparisons, it's very important to compare the same exact things, because sometimes I've seen a lot of people will compare, oh, NumPy indexing operations are faster than Pandas. Like, that's obvious, they are, because they're doing a very specialized thing, whereas Pandas tries to do a lot of inference and a lot of magic on top of this. So these are completely non-comparable. People try to compare them, and they do, and they're wrong. Okay. So this is my, I like this quote. This is by Donald Knuth. Basically, people try to optimize the wrong things. They try to optimize before they even start. Again, we're going to stress that you should profile a code. Okay, these are all just sort of general things. Now we're going to actually get into some specifics of how to make Pandas fast. Okay, first thing is, so if you have two algorithms, Pandas can't help. Pandas reduces the coefficient in front of your algorithm. Whatever algorithm you choose, it'll reduce the coefficient. At least we hope to do that. But if you have an n-log-n algorithm and an order n algorithm, use the order n one. It's not going to help. There are some things to note, though. So here's a simple example. I'm taking a data frame, and I want to know the top 5 values and the bottom 5 values. And naively, we might sort it. Pandas actually comes bundled with an n smallest and an n largest. These do, in effect, an order n. It's not a sort. It's not even a partial sort. You can do that too, but these just scan and get results. So again, I always try to compare things and make sure we get the same result. And you can see in this particular case, you actually get quite a large speed up by doing this. Again, your mileage may vary. If you're using a small frame or a small series, this may not make any difference. It may make it slower. There's more function calls here. Okay. Now, here's actually something that was improved on NumPy. So Pandas has as I said, a hash table implementation of for various uses. One use is unique, actually. Pandas actually can really beat the pants off NumPy. With the further property, uniques are actually done in the same order as they are represented. NumPy sorts, that's why. So not that useful in my opinion. So I almost always use pd.unique. Okay? All right, next. Okay, I'm going to talk about idioms. So if there's an idiom that you can use it. Let's see, let's close these as I don't need them anymore. Okay, oops. So these are two, I'll say, easy idioms that are pretty useful. So people do a lot of group bys. This is the concept of, in fact, this is actually in the docs like this, where you basically will say you'll normalize a group. Basically, I want to do like a z-score type of thing on a group. You can actually unwrap this. So you can use transformational operations where you basically do the same exact thing, but you do this sort of in a, I'm not going to say a vectorized way, but what happens is some functions that, there's a certain subset of functions that are already Cythonized. There was like mean, standard deviation, things like that. They were very fast. So we can use them, and this means this is going right to the Python functions. If you use apply, it can be very fast, but it's not possible at the moment to decompose this UDF, this user-defined function that you're passing. So this is in effect done almost in Python space. That's why it's much slower. So if you can unwrap your group bys. And in this case, I'll stress in this case, we get a pretty good speed up. Now, the case I'm giving you here is, I think we have, what I have, 1 million elements here, and I have, up here, and I have 10,000 groups. I'll do another case where I only have 100 groups. Doesn't help much. Why? Because there's overhead with doing some of these operations. And again, your mileage may vary. Another simple idiom is if-then. I have seen this so much. We'll talk about apply in depth in a few minutes, but this is just painfully slow. You're basically doing a loop here. Anytime you're doing apply, you're more or less doing a loop. Think about that. And you're in Python space almost the entire time. So there are built-ins where to do exactly the same thing, and you can get quite a nice speed up doing this. Okay. All right, going back to my slides. So again, I'm going to reiterate, you should use the built-ins and vectorization as much as possible. You just always think vectorization. It's the same with NumPy. Always think vectorization first. So I'm going to show you some specific code here. Let's see here. Okay. So I'm going to do basically a bunch of different computations using various methods, and you'll see, and I'll explain why some are faster than others. So we're doing almost a trivial computation here. We're taking one column, multiplying by a scalar, adding another column, and then we're adding one to it, and then we're doing a reduction operation. We're doing a sum. Okay. Here's the Pandas code. NumPy code looks pretty similar. I'm using this dot values, and I'll go through that in a few minutes. In effect, a dot values on a series will just give you back the NumPy array. We're going to try the same exact thing using numExpress directly. Again, you have to actually use a string expression here. And we'll do it using bottleneck. Further, we're going to use an actual Python routine to do the same exact calculation. And we're going to use a number routine to do the same exact calculation. One thing to note, Python and Numba both take NumPy arrays directly. They don't operate on series or data frames directly at the moment. They might in the future. So I'm wrapping these with a little function just to return. Actually, I'm not doing that here. I will do that in another example. I'm calling with a function here. That's what I'm doing, just to make it even performance. Again, I'm doing an assert effectively here that these are all equal values to some precision. So, results. NumPy, you get, decent performance. Pandas, you actually get slightly better performance. The reason is this actually is going out to bottleneck, interestingly enough. NumExpress itself, you get quite good performance. Using bottleneck itself is not great in this case, or it's pretty similar. And I said before, for this expression here, we're actually going out to bottleneck. We don't actually use the bottleneck. If you think about it, most of this actually is a NumPy operation here. So it's sort of so the test I'm doing on bottleneck is actually a combination. So it's not a good test of bottleneck, but I just stuck it in there. And of course, if you look at the bottom two numbers, a custom Python routine and a custom number routine actually beat the pants off of all this. Well, you'd be like, okay, we should just write everything in that. Well, no, because for the most part, this is pretty. It's much nicer to write this kind of expression. It just is. And when you have a critical part of the code, okay, great. Drop into Python or drop into Numba. Fantastic. It'll work. Okay. I'm going to also give you just a very brief next notebook here. This is very similar to the last one, except I'm doing a specific example here. This is something that right now is just basically impossible to do in Pandas because, so I'm going to model a recurrence relationship. And in fact, I'm going to model a particular one. This is EWMA, exponentially weighted moving average. The reason I'm doing this very specific one is because Pandas actually has an implementation of this. It's not completely general, though. It's very specific. It takes like one parameter. However, there's lots of people who want to do something very general. They want to write their own recurrence relationship. And right now in Pandas, you cannot do this. You can, but it'll be painfully slow. So I'm going to give a Python implementation here. And in this case, actually, I also have a Python implementation right here. And I'm doing what I said I was going to do before, which is I'm wrapping these things so they look like they're the same exact object coming out. I'm wrapping them in a series. So I'm passing in NumPy arrays, and then I'm wrapping them in a series to come out. Okay. I'm doing the same thing. Here I'm just simply calling the pandas routine, pd.ewma. Okay? I'm doing the same thing with numba. And you'll notice the code, the Python code and the numba code is very much like the Python code. Now, this is sort of a well-known phenomenon, I think, at this point. And this is the beauty. You can just literally copy and paste your code, stick a decorator on it, and you get numba output is great. You have to be really careful, though. The one problem you're going to find with either numba or Python is that if you try to pass in a series, number one, it won't work with Python. It'll actually work with numba. The problem is, and I've seen a lot of people, they go in and they try to index into this. That is a problem at the moment. It will simply not work. You'll be pushed back into Python mode. So you just have to be really cognizant of what you're doing, really work solely with NumPy arrays. You can pass in the index if you want, and the values. Now, this may be addressed at some point in the future where number can actually deal with the indexing part. But just keep that in the back of your mind. Okay, so results. Again, I'm looking for correct code. And I'll do some timeouts over here. And we can see that Python is painfully slow. The Python implementation is pretty fast, like under a millisecond. The number implementation is also very fast. This implementation actually is what we're using in Pandas. And you say, oh, it's really slow. The answer is this is actually doing a lot more work than the Python implementation I wrote up here. It's doing things like NaN checking, very important thing. But for the example I used, I didn't put it in here. All right. Okay, next slide. So we've discussed how to make Pandas fast. Now we'll discuss how to make Pandas slow. In other words, these are things you should not do. So don't use apply unless you really, really, really have to. This is evidenced. This was a quote somebody gave me. If you think you need to use apply, think again, and then think again about it. And then, okay, if you really, really, really need to use it, great. But it was put there, I think, for convenience. Turns out to be convenient but not performant. So you just have to be really cognizant of this. Apply. I see all the time people are reaching for apply. Apply is the last tool you should reach for, not the first tool. Okay. So second thing. Okay, I need to iterate because I don't know how to make a vectorized algorithm. Okay, so I'll use iter tuples or iter rows. Avoid these two. If you really, really need to iterate, you can use iter tuples, and we'll show that in a couple minutes. And I'll explain why that is in the next 2 slides. Third thing not to ever do, iterative updating. I'll show an example of this. This is, in some sense, this is a Python pattern. And however, it's an anti-pattern when you get to Pandas. Or for NumPy, this actually may work. But for Pandas, this is completely an anti-pattern because it's somewhat expensive to individually index elements. And I'll show you why in a second. Okay, so now we're going to go through another little notebook I have. Let's see. So, how to make, well, yeah, this is supposed to show up slow. Oh well. So I did a bunch of benchmarks here. And basically the code is here. Here's our baseline code. This is a vectorized code. We're just adding one to a series. Easy. Here's the apply. Code looks simple. Iter tuples. Now, the one thing to note here is we're iterating over a tuple, so we have to index now by position. Okay. In some sense, that may be fine. Iter rows actually gives you a series back, and this is the reason it's actually, in this case, actually it doesn't. It gives you, I'm sorry, it does give you a series. This has 2 bad properties, and this is why iter rows is slow. One, it has to consolidate the entire D type of that row. Now, in this case, that's cheap because it's actually a float. All your D types are floats. If you have non-floats in there, it becomes extremely expensive to do. Okay. Here's another example. This is indexing. So I'm using an indexing operator, ilock or lock or ix, to actually set values in place. Looks like okay Python code, but in Pandas this becomes painfully slow. Even worse is I'm indexing and then I'm creating something at the end. Okay, again, I'm going to assert that all these results are true, that they're equal to each other. Our baseline is quite fast. Itertriples is not bad, actually. Apply becomes painful, more painful, really painful, and a lot more painful. So here's the little graph of that, and I was going to do this originally on a log scale, but this looks fine. So the answer is, if you're doing anything but vectorization, you shouldn't be. If you need to do something, a calculation that is very hard to vectorize, then you need to reach for another tool. Reach for Cython or reach for Numba and hook it in. That's the way to make Pandas fast. Okay. I'm going to show one more notebook. I was talking about before, people like to compare NumPy and Pandas for indexing, and this is a mistake, and I'll show you why. So here's a bunch of different indexing operations. All we're doing is setting a single element. We're using IX, lock, and ilock. We're also using at and iat, which are specially made for this type of single element updating. In NumPy, we're directly updating the value. So you can see that ilock, ix, and lock are, the same order of magnitude here. At and iat are significantly faster, and NumPy is faster still. Okay, great. Does this matter? I had somebody argue with me about this, like, oh, this 2 microseconds actually makes a difference. I'm like, well, do this example here where we're gonna iteratively update a NumPy array. We're gonna do the same thing with a data frame, and then we're gonna do a vectorized indexing operation. So, okay, NumPy's pretty fast. Using, it's pretty slow actually, but it doesn't matter if you can vectorize your calculation or vectorize your index setting method. So yes, this might matter to you, but if you're doing it this way, I would just say go right to Cython or go right to Numba. If you do need to do that, and there are cases where you do need to do that. Okay, next. Oops. Shoot. Okay. Dot values. So this is a double-edged sword, like the nice graphic there. I explained before that you could you can actually access your NumPy array directly from Pandas. You can take your series and do dot values, you get a NumPy array back, great. You can also do this with a data frame. However, with a data frame, this is a big problem actually, because what it will do, it'll coerce all your D types to a common D type. And if it's like ints and floats, that's okay, it still might be fine. However, if you have strings in there, which we all have strings in there, this is a big problem. It makes everything object D type. I'm running out of time, so I'm going to hurry up here. So the point is, dot values can be great if you want to directly access, say, a series. If you want to access the entire data frame and you have strings, it's a problem. Object D type is there to satisfy the need of everybody because they want to have objects. But if you want performant code, you need to avoid them. Okay? All right. Going to...
We need to finish by 2:05.
Oh.
Including your question time.
Okay, fine. Okay, so I'm going to go over some do's and don'ts. So, do's, have the correct D types. This means don't use object D type if you don't absolutely have to. And we'll discuss strings in a minute again. But my point is, don't represent floats as object D type. There is no reason to. Don't put actual objects in a data frame or a series. You don't need to. And if you really do, you're doing it the wrong way. Use pd.concat. So this is the way to, it's very similar to np.concatenate. Basically, I mentioned before that there is a, if you want to do lots of insertions, again, you're doing it the wrong way. Instead, what you want to do is construct sub-data frames, say, concat, boom, one copy altogether, it's easy. I don't really have too many examples of these, but I will, for these particular things. Categoricals, use them, and I will, again, I'm going to defer this just a second. Use the idioms and built-ins, we already talked about that. Apply is actually okay in certain cases. In other words, if you're applying across columns, you have some cool function that works on a vectorized input, a 1D array, and I just want to apply it across my columns. Okay, that's perfectly okay. It's a nice idiom, actually. Okay. Here are the don'ts. Repeated assertions, we just talked about this. This can, anything that can cause repeated copies is a problem. Don't repeated inserts. Don't micro-optimize. In other words, don't try to set elements individually in a data frame. If you have a few to set, great. If you have a lot to set, don't. There are various methods of updating if you have lots of these. Don't try to loop over things and do that. So don't use loops, don't reinvent the wheel. We already talked about apply. Apply map is a similar concept. It's again a convenience feature that is in effect sort of like a ufunc type mechanism where you can do something to every single element in your data frame. We have ufuncs for that. However, apply map, as I just originally was conceived, I think, as just a convenience feature for that. So this is a hard one, actually. Nested group by apply. So group by is fine, apply is fine, and then I've seen a lot of code where people actually nest them inside the apply or do some complicated function. So as we saw with the unwrapping group by, it can work. You can certainly do whatever you want, but the problem is a lot of things are just simply not performant if you continually do functions inside apply. So you try to want to minimize the number of function calls you're doing or the complicatedness of that function. So hence don't nest group by applies. And I'll suggest, I don't have an example here, say you were doing this. What you want to do is you say you're grouping by things, and then in each group you want to do another group by. That is just a multi-group by. So there are various ways to pull these things out. A few versions back, in place was added, and in my opinion it was a mistake, but it was added. In place doesn't help you. Everybody thinks it does, but it really doesn't. There's very small subset of cases it actually will. In general, in place is implemented. So this is an operation. You know, almost all the operations have an option. In place equals its defaults to false, but people set it to true and it's like, oh, this is great. It's gonna make it faster. No, it doesn't. In fact, all that happens for most of these operations is we do the operation on a copy and then shove it in there, and you get back the original object back. It doesn't actually help. And in my opinion, the real reason not to use it is it just makes your code it doesn't look as good. You can't chain things. You can't pipeline things. So in my opinion, there's never a reason to use in place. There just isn't. Okay. All right. So now we're going to talk about memory for a couple of slides here. I will endeavor to hurry up here. Okay. These slides are, by the way, they're all available here with the notebook, so you can obviously look at them. So very common things to do data conversions. Here's an example of I have maybe a weird string format of some dates. I have in year, month in this case. Okay, I just created it here. This doesn't, annoying. Doesn't scroll properly. Okay, well, whatever. So 3 methods of actually parsing this type of string. Here's a method, I've seen this a lot. Again, this is doing a vectorized function. You're iteratively applying a vectorized function, okay? That's called the slow way. The regular way is simply to put it in with a format. However, actually, Ian made this point. If you can convert your strings to ISO 8601, you can get massive speedups. This is implemented in C, the parsing of these. Even some non-ISO 8601 strings can be parsed. But for the most part, if you can coerce yourselves to a reasonable date format, you can get massive speedups in the parsing, okay? And we can see here, slowly, faster, and even faster, okay? So my point is that passing format essentially is a regex parser. However, some of these formats can be, or have speedups implicit in them, okay? And I'll show this in the next example as well. Read CSV, use it, full stop, okay? But you come into a lot of cases where you also have dates, and this is you have weird date format here. I just created this one, okay? And people say, okay, use date parser. There are times to use date parser. Limit them. Generally, this is also done in Python space, so it's generally not a fantastic idea. This next way of doing this is I'll call regular parsing, where you just give your you just say, hey, parse this column. This works fantastic if you have 8601 strings. If you don't, you'll be surprised at how slow it is. However, there's a new keyword that was introduced called inferred datetime format. For a lot of pretty common formats, this provides automatic inference of your formats, caching of them. So it'll be, if you have all the dates of similar formats, This is per column. It'll provide nice speedups. And the last thing is, the last example here is, in general, actually defer date processing as a post-processing step. I will just simply read in my dates as strings, and then I will process them afterwards. And the reason for this is I have a little bit more flexibility here. I can do various operations. Maybe I need to do a substitution or something. I might want to do it in a, use some of the string operations to make them very performant, because they are very performant. Maybe I have to substitute, get some weird character out of that or something, and then I will process them. So I oftentimes defer date processing to a step after I actually read the CSVN. So here's the examples for these. And they're not terribly different in this case, but date parsing, I actually wanted to make it worse, but it actually turned out okay in this case. And you know, it's a simple loop, but it was fine in this case. As you see, regular parsing is just painfully slow. You know, it's because it's using regexes internally. Even though it's in Python, it's still using regexes, so these can be slow. All right, next slide quick here. Categoricals. So these were just introduced in version 15, and these are an awesome feature. In effect, what is a categorical? A categorical is a mapping of something, usually strings, but it doesn't have to be, to integers. Okay, and then we keep a map of what these integers represent. For duplicated data, these are fantastic. They have two amazing benefits. One, storage space. They take much less to store. And two, they get you out of object land. They make your manipulations be on integers. This is fantastic, so use them. So here's a quick example. I'll create, they're very easy to create. So you just, you have strings. We created a string object, and we're just as typing the category. This is I'll call it a pseudo numpy d type. Here's the example. So memory usage of the object, you know, say, oh, well, that's not too hard, but this in reality is not even your real memory usage. This is actually your real memory usage. Because if we're going to do this in Python land, okay? In NumPy, your real memory usage is here, okay? Because what is an object array? An object array is just simply a pointer, takes 8 bits, or 8 bytes, and to some memory space where it's keeping it, okay? So Python using strings is bad. It just takes a lot of overhead per string. NumPy is better because all it does is that actually it keeps it as a fixed memory block, so it's actually not terribly inefficient. However, once we go to categoricals, we can reduce your memory usage dramatically. So example for this example here, all we have to do is store, this actually only stores an int 8 for the column, and then 40 bytes or whatever for the actual strings themselves. So this will have tremendous savings on your in-memory usage and your on-disk usage, and that's what we're going to show now. So I write things to HDF5 a lot. We implemented this also. You can actually store, so this is storing as a fixed length string, storing the strings, and this is storing with the categoricals. So you get a quite nice savings there. Okay, next slide here. Okay, next thing I always suggest to use are iterators. Whenever you want to read from, say, disk in a CSV or an HDF5 format, you can do this with other data types as well, other formats as well. You should use iterators. Why? It guarantees you a constant memory usage. You'll only use a certain block of memory. You have a data frame that you can use. You can do whatever operations you want, and that's a good thing.
Okay.
Yes,
5 minutes
I know.
non-stop. If you want to take questions, you can do that, or you can carry on.
Yeah, I'm going to finish in 5 minutes. We'll take questions afterwards. Okay. The other thing I wanted to put in is use columns. So this is a fantastic way to read a very wide CSV as an example. This is very efficient when it's reading a small number of columns. So that's a good thing. Interestingly enough, with HDF5, this actually is not as easy to do because it's a row-oriented format, and selecting out columns is actually hard. So you'd be surprised. The memory usage of this, people have been surprised, is the same, okay, as if you're selecting the entire row. It's just an unfortunate problem in HDF5. You can actually select out a single column very efficiently. This is actually quite efficient, but selecting more than one is just not supported at this point in time. All right, one more slide here. Okay. I'm going to skip this slide, but I will just point you guys to various ways of thinking about serialization and I/O. There's a couple of links I have here to this fellow Matt Rocklin, who developed Dask. We're going to talk about that in a second. He did a nice study on the cost of serialization of various data types. So that's on my slide as well. Okay. My last slide, or last. So, global interpreter lock. Right now it exists in Pandas. In version 17 it will not exist. We are going to release it in all Python code. It wasn't actually that hard. This was actually at the prodding of various people, because the reason is you can get nice threading speedups. I never recommend, I haven't talked about threading at all, and I barely touched on multiprocesses because most of your data doesn't need it. If it does, now you'll be able to do it. You'll be able to use threading models and multiprocessing models in a very nice way. Okay, next slide. So, you know, everybody's like, oh, out of core. Pandas really doesn't support out of core at this point in time. Again, I will touch on something that does. There are various ways around this, but we're not going to talk about them here. Okay, so my solution right now, this is a very new open source library called Dask, and it will allow you to effectively, it uses Pandas internally. In fact, we wrote some specific features for this to enable threading, multiprocessing, and distributed computing using Pandas, and it's a very similar API. Okay, and we may build this actually into Pandas where you can actually take your computations and defer them right out to Dask. Right now you can do the opposite. You can use Dask arrays to basically give you nice Pandas frames. Okay, that's it. You guys can contribute, and this talk again is on that on GitHub. So I don't know if I really have time for questions, but I will be here afterwards. And that's it.
2 minutes for questions.
2 minutes for questions.
Do we have any questions? We've got one with Amit, but I'm going to ask a question first.
Sure.
The inferred date times, datetime parser, does that deal with month, day, followed by day, month examples?
You can actually pass.
I don't want to tell you what the answer is.
The answer is
for me.
that could be
we have it in funny order.
Yes, I know. I know. Basically, what inferred datetime format does, it deals with things like you can put whatever separators you want between the various fields. It still has to be a regular format, though. Any other questions?
There's a regular format. Day,
Yeah, whatever.
European.
Oh, sorry. I'm sorry. You didn't ask a question. Go ahead.
Yeah, you hinted a bit on out of core there. I wanted to know what are your thoughts on how Blaze plays with Pandas, and
Sure.
What are your suggestions there?
Okay. So, again, some of my other fellows I work with, they wrote Blaze. So Blaze plays very nicely with Pandas, actually. And again, that's another solution to dealing with out of core. Blaze, just for people who don't know, Blaze is basically, if you think about it, it's a way to construct in Python a lazily evaluated expression. And then you can set it to a computation backend, one of which could be Pandas, okay, to actually evaluate it. But it's nice that it's lazy in its evaluation.
And then we should finish there, so we have time to swap over for the next speaker.
Sure.
So let's thank Jeff.